Welcome. In this video, I'm going to show you how to run computations on your GPU using OpenCL and C. I expect this video to be fairly long because we are working at a very low level here and there are a lot of details we need to handle. But let's get started. Now, we have to write two programs, a special program called kernel that runs on the GPU and another regular program that runs on the CPU. This program is responsible for sending the kernel and all the data to the GPU. So I'm going to call it host.c. We'll be printing stuff and reading files, so include stdio.h. And we are working with OpenCL, so include OpenCL.h. Create a main function. We need to get the GPU first, so create a variable of type CL device ID and call it GPU. And initialize it by calling get device IDs. The first argument you pass here is the platform ID, which can be null. The next is the type of the device you are interested in. So this will be CL device type GPU. Then we want one device ID, so say 1, and then pass the address of your GPU. And lastly, pass null again. This should be good. Next, we need to create a context, a compute context, so call it CL context. We also need a variable to hold the error codes that these functions could return, so call it result. And now we initialize the context by calling CL create context. The first argument is a list of context properties, but we'll say null and use the default properties. Then it's a context for one device, so say 1, and then pass the address of the GPU. We don't want any callbacks, so say null. We don't have any user data, so say another null. And lastly, pass our result. So if the result is not equal to CL success, then let's print couldn't create context and exit. I'm gonna try to compile and run. So pass OpenCL as the framework and just say host.c here. Okay, no errors. Now you need to create something called a compute command queue. So it is a variable of type CL command queue. And I'm going to call it queue. And we initialize the queue by calling CL create command queue. The first argument is the context, then the GPU, and then 0, because there are no special properties we need, and lastly the address of the result. We could check if the result is CL success again. Yeah, let's check. Here we can say couldn't create command queue. Okay, let's try to compile. No errors. The next step in the host program is to pass the kernel to the GPU. So let us create the kernel now. We'll just be working with a one-dimensional array here and perform some simple mathematical operation on each of its elements. The code that runs on the GPU is written in a language that resembles C but isn't really C. It adds a few function and variable qualifiers to the language. The first function qualifier we'll be using here is kernel. Then you define your function as usual. I'm going to call it square root. You need to be aware of the address space your functions, arguments, and variables use. We'll be working only with the global address space today, so say global here. And then we are going to be having an input array of floats and an output array of floats. While working with the GPU, you obviously do your calculations in parallel. And that means we won't be writing a for statement to loop through the array. Instead, we just need to get the current index of the loop. And to do that, you have to call a function called get global ID. To this function, you pass the dimension of the data you are interested in. Ours is a one-dimensional array, so we have only one dimension, and that's 0. Once you have your index, all you need to do is say out of ID equals sqrt of in of ID. Sqrt is a built-in function in OpenCL, so you don't have to include anything to access that. And that's it. That's our kernel. We are ready with the kernel. So back to our host program. Here we now write code to read the kernel, create a program with it, and then build the kernel. So first, let's read the kernel. To create that, so to do that, you create a file pointer, and then use fopen to open the kernel file in read mode. Oh, and you also need a character array to store the kernel. So I'm going to call it kernel code. Let it be 1024 bytes. And then I just call fread and pass kernel code. Let's read one character at a time, a maximum of 1024 characters, and then fp. At this point we should be having the kernel code, so close your file. And let's just print the kernel code just to make sure that we didn't make any silly mistakes here. Okay, no errors. Good. So time to create a CL program now. This will hold the kernel code. To create the program, you say program equals CL create program with source. Pass the context first, then say 1. And now we need to do some typecasting here because we need to pass an array of strings here, but we have only one array. So say const char star and then array, and here we say kernel code. our string is already null terminated, so say null here, and finally pass the result again. Let's check if we still don't have any errors. I'm just going to say couldn't create program and return 3 here. Let's see if this worked. Yep, still no errors. So we can now build our program. And to do that, all we need to do is call CL build program and pass the program to it. Then say 0, which means there are 0 devices in the program itself, and then pass null because we don't have a device list, another null because we don't have any custom build options, and another null because we don't want any callbacks, and another null because we don't have any user data. This returns the result, so we can just get it here. And if the result is not CL success, that means something's gone wrong with our program and with our kernel code. Couldn't build program. I hope there are no errors. Okay, we have no errors. Now you see that our kernel function takes 2 float arrays. So let's get back to the host program and create these 2 arrays. I'm gonna initialize the input array with just 3 numbers. And they are going to be 9, 25, and 64. And the output array is going to be equal to 0, 0, and 0. It will be easy for us to verify the results with these simple numbers. Okay, now that we have the input and output arrays on the host, we need to create OpenCL buffers for these arrays. And these buffers are going to be of type CLMem. And I'm going to call it buffer in and buffer out. To initialize the buffers, we have to call a function called CL create buffer. Let's start by initializing buffer in. Yeah, buffer in. So call CL create buffer. Pass the context first. Now this buffer is going to be a read-only buffer, so say CLMem read only. Then get the size of float and multiply it with 3 because we have 3 numbers. Then pass a null because we won't be passing a host pointer. And finally pass the address of result again. Now we check for CL success. And print couldn't initialize input buffer. And return 5. I'm going to compile and run again. Okay, no errors, so we can proceed. We have to follow the same process to initialize the output buffer. So I'm gonna yank 7 lines and paste them. This is gonna be 6. This is gonna be the output buffer. This is of course going to be buffer out, and here we say write only because the output buffer is a write only buffer, and everything else stays the same. And I'm not going to check again because this should work. Okay. Now we need to write the data that we have in our input array into the OpenCL input buffer. To do that, call clnq write buffer. The first argument is the q, then pass the input buffer, and now this can be a blocking write operation, so say cl true, and the offset is going to be 0, and again the size of our data, so it's size of float multiplied by 3. And now we pass the input array. We are not going to be dealing with any events in this code, so say 0 for the number of events, and pass a null for the event wait list, and another null for the actual event. This function returns an error code, so assign it to result. And now you know the drill. Just check if result is not equal to CL success. And I'm gonna say couldn't enqueue write buffer. And return 7. Compile. We don't have any errors. Okay, so this is good. Now that we have our data ready, we need to select the kernel from our GPU program. We have only one kernel, but we still need to do this. So create a CL kernel variable and call it kernel. To initialize the kernel, call CL create kernel and pass the program to it. Then the name of your kernel, which in our case is square root, and pass a null. Now that we have the kernel, we have to set its arguments. Our kernel takes 2 arguments, remember? So call cl set kernel arg and pass the kernel to it. And now we are setting the first argument, so say 0. And this argument is of type clmem, so say size of clmem. And then pass the address of your input buffer. Repeat the same to set the second argument, but say 1 here and say buffer out here. And now to actually run the kernel, we have to call a function called clnq nd range kernel. Nd range here just means n-dimensional. Our data is 1-dimensional, so it's going to be a simple call for us. First pass the q and then pass the kernel and the number of dimensions we have, which is just 1. Then the global work offset, which can be null. Then the number of elements we have in the input buffer, and that's 3, but we cannot directly pass 3 here. We need to create a variable of type size t. So So let's just create a variable of type size t and call it count and make it equal to 3. And now we pass the address of count. Then we pass a null. And we are again not dealing with the events, so say 0 null null. This is going to take a while to finish, and we want to wait, so call cl finish and pass the q to it. At this point, our output buffer will have the calculated results, but we need to read those results and put them into our output array. To do that, call cl nq read buffer. Calling this is very similar to calling the nq write buffer function. So pass the q first and then the output buffer. This is again a blocking operation, so say cl true. The offset is 0 and then pass the size of the data, size of float *3. We want the results in our output array, so say out. And again, we are not handling events, so say 0 null null. Okay, at this point we probably have the results in our output array. All we need to do is just print them, and we have to loop through them. So let's create a variable called I. And now we can write our for loop. And I'm just going to print with %f/n and out of I. That's it. Let's try to compile and run. Okay, so yeah, it seems to have worked. We have the right results. Our data, our input data was 9, 25 and 64, and we have 3, 5 and 8. So those results are correct. And now you know how to run computations on your GPU. It takes a lot of code, but yeah, now all you need to do is change the kernel or change your data, and you can run all sorts of computations on your GPU. Thanks for watching. Please like and subscribe. Bye.